much, Jeremy. Good afternoon, everyone. My name is Evgeny Gurnevich. I'm from the Directed Energy Research Center from Technology Innovation Institute, Abu Dhabi. And my today's talk is devoted to one of the projects that our research center is currently working on. So the topic is millimeter waves for drilling in oil and gas and geothermal industries. So why do people drill holes in the earth? Obviously, it is required for the oil and gas industry and, for example, to access underground water sources. But there are other applications of drilling, both purely scientific and practical, like, for example, nuclear waste storage in deep holes. But let me highlight the actively developing direction of geothermal energy sources. As is well known, the temperature underground increases with increasing depth by about 25 degrees per kilometer. So the main idea is to pump cold water or another coolant like liquid CO2 from above into a deep well, where it will be heated and rise to the top in the form of steam and hot water. The rest should work in the same way as for all modern power plants. At the same time, in order to significantly increase the efficiency, it is desirable to have the highest possible water temperature, because especially at 373 Celsius and 220 bars, the normal water becomes supercritical and its heat capacity increases rapidly. That is why achieving high depths, let's say 12 kilometers and even more, for enhanced geothermal sources is very important. So what could modern technologies offer? Of course, mechanical drilling. This technology is fully mature and has all the benefits that this entails. But there's many drawbacks if we want to drill really deep. Like big improvements for this technology are unlikely. The drilling is slow in hard formations, and the cost and drill rate both decrease exponentially with drilling depth. One of the alternative technologies is millimeter wave drilling. Let's start from the basic physical principle. Millimeter waves are a part of electromagnetic spectrum with frequencies, let's say, from 30 to 300 gigahertz. It has been experimentally shown that these waves are well absorbed in rocks, both granite and basalt, causing their strong heating up to the melting point and even evaporation. At the same time, unlike laser radiation, millimeter waves are weakly sensitive to the presence of dust in the air and can propagate with weak attenuation over long distances. Additionally, taking into account the well-developed technological basis, here we need to say thank you for researchers working on the thermonuclear fusion, because the most powerful millimeter wave sources are developed and used now for heating thermonuclear plasma. So how are we going to apply millimeter waves to directed energy drilling? The general schematic looks simple. Also, there are many technical problems hidden behind it. One of the key components is the gyrotron. This is the source of high-power millimeter waves. And at the simplest level, a millimeter wave deep drilling system requires only one component in the wellbore, the waveguide, which has only vertical motion of advancement into the hole as it is deepened. The gyrotron energy output and compressed gas are injected at the surface. The rock is melted, fractured, and vaporized by millimeter waves, and the dust and solid particles are supposed to be carried to the surface by the purge gas flow. The reaming of the borehole to a diameter larger than the central waveguide is facilitated by the natural divergence of the beam launched from the waveguide. The photos on the left side show you how the process can look like in the lab for small rock samples and low gyrotron power, about 10 kilowatts. Of course, there are many other technologies alternative to conventional mechanical drilling. Some of them are shown in this slide, explaining why are we concentrated mainly on the millimeter wave drilling. Naturally, the main reason is that with millimeter waves, we hope to overcome some of the limitations of the other technologies. But let me not go deeply in these alternative technologies, since I have only 10 minutes to finish this talk. I would like only to emphasize that the main advantages that are supposed to be for millimeter wave drilling are drill rate, the high drill rate that is supposed to be constant with depth, and drilling cost that should increase linearly with depth, not exponentially. So the advantages of millimeter wave drilling have led to significant investments in the development of this technology over the past 6 years. The key player here is Quaise Energy, founded in 2018. Its activities are based on the research of Professor Paul Woskov from Massachusetts Institute of Technologies from the USA. According to the open data, funding for the development of millimeter wave drilling in Quaise Energy currently amounts to about $107 million. And for example, among the investors in 2024 is such a well-known company as Mitsubishi. Currently, Quaise is building a complex for field demonstrations. The first stage is expected to be a hybrid drilling rig combining both conventional and millimeter wave drilling. And it is expected that this will be done in 2025, this year. Here you can see some of their facilities, how they look inside, like Geothermal, transmission lines, sample chamber for testing the rock samples in the lab. I encourage you to visit and explore their website. If earlier in laboratory experiments drilling was demonstrated on small rock samples, then one of the last achievements, which was reported in 2024, is drilling a 2.5 meter deep hole in basalt. Now let's move on to our first demonstration project in Directed Energy Research Center. The main goal of this project is to design the prototype to implement state-of-the-art knowledge in millimeter wave drilling technology to drill hard rocks. We plan to use gyrotron sources with power levels up to hundreds of kilowatts for this. But at the first step that we are near to finish in the coming month, in the April, we will use 10 kilowatts, 28 gigahertz source, commercial magnetron especially. So this slide shows you what we are doing right now. We already have a gyrotron source on the left. It's not very high power, only 10 kilowatts, but it's enough to melt rocks in the lab. And it's supposed to be placed in customized container in order to be mobile, which is needed for test in the field. And the works are almost done for the chilling system for gyrotron that can support operation in the desert in UAE conditions. And for the very first tests, we've designed test chamber to study all needed millimeter wave drilling processes and technologies in the lab conditions. Now we are finishing the design of millimeter wave transmission line for our system. Some parts are ready now, as you can see in this slide. Some of them are in process of manufacturing, but we expect to do the first shot this April. Let me remind that the main goal of this project is to gain experience and clarify design parameters and tasks for the next stage if we decide to go to it for the full-scale drilling. Of course, achieving this goal implies completing related scientific tasks, developing transmission lines, effective transmission lines for beam, effective mode converters, polarizers, and so on, and the determination of rock properties under intensive radiation, beam, and after irradiation. So, of course, today we are only in the very beginning of our project. This is not something that we finished or not something that we can propose some commercial product. In the coming 2 or 3 months, we are commissioning the first millimeter wave source here in UAE, and Now we are actively working on the design and manufacturing of transmission line components. The first tests are coming. We are excited to start this project together with maybe to compete with Grace and other key players. That's to be short. That's all from my side. I'm open for questions now.